Hello everyone. So today we are going to talk about a string compression algorithm called Burrows Wheeler Transform. To understand this, let's take this string first. Now this string is kind of special. You can see that it has got trailing characters, or it has got the same characters which is repeated consecutively. So it has got us this chain of A, two A's, then B, 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 and then A. Now, if you know about run length encoding, you will understand that we can compress this string, or we can express this string in this way too, 2A, 3B, 2A. And we save space for storing all the extra characters by mentioning how many times that character occurs consecutively. And we can easily, get back this string from the compressed one. Now the thing is that in the small string, you might not see a lot of improvement, a lot of memory saving in terms of percentage. But imagine it's the human DNA, and we've written it in text with ATCG. And imagine if there is a lot of trailing or repeating same characters in there. We can compress it with run length encoding and save a lot of space. But wait, not every string will have this property of this long running trailing characters. The human genome will not have that property. So Burrows Wheeler Transform, what it does necessarily is it takes a normal string and converts it into a string which has this property, or it has got a lot of chance of having this property where we have got trailing characters or same repeating characters. So let's take this string, it and it $. Now why am I using this $? So basically we are using this $, in terms of the algorithm, just to make it clearer, make it easier to use and understand, and we will see how that is. So take this $, as a terminating character. So this $, marks the end of the string, and it is the smallest character of all. What do I mean by that? That means, let's say if we convert all the characters to ASCII codes, $, is such a character which is smaller to all of them. This is just a notation that we are using. Not necessarily I'll have to use I have to append this specific character at end of every string whenever I'm using Burrows Wheeler Transform. But yeah, this is kind of a notation that we use. You can think it of something like a null that terminates a string. Alright. So let's take this string, it and it $, and let's rotate this or do a cyclic shift. So what I have done is taken it and it at $, and then I have rotated it. So the $, comes first, and it at, and we will repeat this process. So t will come at first, so t $, it and it a. Then the a will come here, so at $, it a n I t. And we will continue this process. We will keep doing it. So we will do the shifts as many times as the length of the string. So you can see I have done it here. Each row of this matrix that you see, now I have done it in the matrix format so that it's clearer to read and understand. So in this matrix, you will see each row is the rotation of the string. So I start with it and it $, and then I have rotated the string. You can see the dollars make this diagonal, so that means I've rotated that string each time, right? And we will do this at the same amount of times, which is the length of the string. So each position will have all the characters at least once. What do I mean by that? That means this in this matrix, each column is a permutation of the string, which is quite obvious because we are rotating the string, right? So each position will be visited by a character of the string at least once. right? Now the next step that we'll do is we will take all the rotations of the string that we have made, all the rotations, and then we will sort it. So we will take each row of this matrix as a string and then sort these rows. So we get something like this. So you can see the first row that we have, the first string that we have in the matrix is $ITAN, because dollar is a character that is smaller than all of these characters. So naturally, the smallest string lexicographically would be the string that starts with $. And from this matrix, from this list of strings, if we take the last column, this is our Burrows Wheeler transform. Now you can see from this string, in this Burrows Wheeler transform, we have got trailing characters. So we converted our string it and dollar to TTT $NAAII, and then we can run length encoding and compress this string. So we take that normal string, we convert it in such a way that we have got a lot of trailing characters. This is like just best thing about this algorithm that I like is this is so simple, and yet this is so beautiful, and we will see the beauty even more when we discuss how to decode this string, how to get back the original string from the compressed string. So let's start on that path now. To go to the path, let's get some basic intuition. Let's understand some things. So as you can see that this this column that has been taken as Burrows Wheeler transform is obviously a permutation of the string, right, of the original string, and not just the last column. Every column is a permutation of the string. Now, why is this last column special? For that, we have to take a look at the first column. Now, as we did, we rotated the string and we sorted it, right? And due to those cyclic shifts and then the sorting, the first column is always all the characters of the string in a sorted manner, right? And that obviously makes sense because we have sorted it according to that. So as I said, every column is a permutation. The last column is taken as a Burrows Wheeler transform, and the first column is all the characters of the string in a sorted manner. And this is where the beauty starts to show its form, of the algorithm, that we are only storing this column as our transform, as our result string, right? Now look at this. Because these are rotated strings, we know that in the original string, this T character will be followed by $, because dollar follows T in the original string. And how do we know that? We know that because this is a rotation. We know that whatever comes at the last is followed by whatever comes at the first position of a particular rotation. That's how rotation basically works. So in every row we see that this T also is followed by some A. This T is followed by some A. So you might think that we are storing just a random permutation, but no. If we sort this permutation, we will also get the characters which precede this character, which follows these characters. So essentially, by storing this permutation, we are not just making a random permutation with trailing characters, but by storing one character, we are actually in essence storing pairs of characters, because we can easily get which character follows them by a simple sort. Now this is a simple intuition that you need to keep in mind when I will discuss about the decoding, and we will come to the decoding shortly, and this is the base for it. So you might see that I have written this string with some subscripts, and these subscripts are essentially there to differentiate between similar characters, and so that we can study this algorithm more easily. So you can see I1 is here, I2 is here. So I have to not mix up which character we are talking about from the string. I have just numbered these characters. So I1 is here, I2 is here, T1 is here, T2 is here, A1, A2, and T3 is also here. And there is only one instance of n, so we have only n1. And this, I think, is called the T ranks of the characters. Terminologies may not be so interesting and may come later. What is more important is the concepts. But yeah, it's good to remember the terminologies to communicate it better. So I've taken that matrix that we had, and I have because we need to only talk about the first column and the last column, that's why I've graded everything out in the between, and all the magic, all the play that we'll do, it will be only considering the first and the last column. And again, we can get the first column by sorting the last column, and we only have the last column stored with us. So a very interesting property that is in this BWT, you can see that in this first column, the order of the T's are T3, T1, and then T2. And in the last column too, T3, T1, T2, A1, A2, A1, A2, I1, I2, I1, I2. So does that mean that the character order in the character order of same characters in the first column is maintained in the last column? And this may sound like magic, but this is what is happening, and there is a very simple cause why it's happening. Again, another beautiful point about this Burrows Wheeler Transform algorithm. And why is that? So let's think for a moment. Let's take this T3. We are sorting each and every string, right? We are sorting each and every row. This T3 has its place in the matrix because we are sorting according to all the things that are left of it, and this T3 in the first column, we are sorting to whatever is in the left of it. And you can see both the times this string and this string is same. And why is that? Because this is a list of sorted cyclic shifts, or sorted rotations of the string, and that's why when T3 is at last, whatever precedes it is the same as when T3 is at first, what succeeds or what is after it. I will request you to take a bit of pause and think about this, so that it will make absolute sense, and it will be absolute clear in your mind. This is very simple, but it just takes a moment because it may seem like some magical coincidences, but it's actually quite obvious in this case. All right. So once we have that in mind, that the order of the repeating characters, the same characters from the first column, is preserved in the second column, we can do this. We can actually change the way we are ranking these characters just for simplicity. So what I've done is I've just said A1, 2 here, I1, I2 here, N1 and T1, T2, T3 here, and the same order will be preserved in the last column. So T1, T2, T3 here, N1, A1, A2, I1, I2 here. And I've done this just to make things simple. And this is, I think, called B ranks of the characters. All right. Now let's come to decoding it actually. All right. So you can see I have taken the first column and the last column. Initially we'll only have the last column, but we will move ahead and sort them and get our first column too. Now we know for certain that the string, whatever we have, ends with a dollar sign, right? Because that's the rule, that's the base that we are working on. Okay, now how do I understand which character precedes dollar? So how will we understand that? So we'll take dollar from the first column, and we know, okay, what we are dealing with, these two columns, first and last column, are actually rotations, right? So in a rotation, whatever is in the last column of any rotation of a string, whatever is in the last column must precede whatever is in the first column. So we now know for certain that dollar is preceded by T1, because again, cyclic rotations, and then we have sorted. So that's why you see that rotations, making those rotations were so crucial to the foundation of these algorithms, of this algorithm. That's why all this magic is taking place. Cool. Now we know that dollar is preceded by T1, so I'll just append T here. Okay. Now that I know the dollar has been preceded by T1, where can I find T1 in this first column? Now why do I want that? I want that because if I check the first column for the same character, for the same T1, then I know what will precede it from the last column. Because again, as I mentioned, rotations, and that's why last column precedes first column. So we will try to find where is T1. T1 is here, and we know that A2 will precede it because it's in the last column. So A. Then let's search for A2. A2 is here, and we know that T3 will precede it. So T. And let's search for T3 here, and we can see, well, T3 is here, so it will be preceded by I2 or I. Let's search for I2. I2 is here, and that will be preceded by N1. Okay. Where is N1 now? N1 will be preceded by A1, and we append A. A1 will be preceded by T2. We append T. T2 will be preceded by I1. We write I, and that's the end of our string. And how can we know that our decompression has completed? Because I1 is preceded by dollar. That means we are reaching the end of the rotations. And voila, we have got the original string. We have decompressed it successfully, and kudos to us and the algorithm, of course. So we can actually claim that the decompression algorithm takes O(n) time complexity. And you will say, well, you were stupid, because sorting itself takes O(n) log n, right? And you just said that we have to sort the last column. I'll say no. I am stupid, I may be stupid, but in this case, I'm right. Because you see, BWT is used in applications where there is a finite set of characters, finite set of possible characters. That might be 10 characters, that might be 50 characters, that might be 256 characters, but finite. And in these cases, we can easily use counting sort. Now, if you know about counting sort, that's well and good. You understand exactly what I'm talking about. But if you don't know, it's a kind of a sorting algorithm that we can use to sort stuff in O(n). When we have got a very small set or a small set of finite characters, or like, let's say, the possible characters that can be in the string is not very large, then we can use counting sort. If you don't know about it, I'll suggest that you just take a tiny look at that, pausing this video. That will be a bit helpful to understand the intuition behind what I'm talking about. Alright, so let's go ahead. So let's get a little bit more refined algorithm to for the problem, for the decompression, which will give us a little bit more edge when we are writing the code. And we will not write the code in this video. That will be left as an exercise for you guys, but we will try to understand how we can do that. So as I was talking about that, we have to search this t from this first column. So let's say we have t1 here, we will have to search where is t1 in this first column. Now that might be a problem, because that will itself take our algorithm to O(n) square. So how can we prevent that? So first let's just calculate the ranks of the characters. So 0, 1, 2, 0, 0, 0, 1, 0, 1. And why we have done this? Like we were writing ranks of 1, 2, this is just those ranks but 0 indexed, right? Let's make another small table with AINT, all the distinct characters, and we will store their counts. So it's like a map. So we will say 2, 2, 1 and 3, because A occurs 2 times, I occurs 2 times, N once, and T 3 times. In the first column, the first A will be after 0 characters, right? Because nothing can precede A. The first I will be after at least 2 characters, because we know that at least A will precede it, right? So the first I will occur after 2 characters exactly. N will occur after 4 characters, because A and I will precede them, and the first T will occur after 5 characters. And then we can see that, wait a minute, we were talking about counting sort, but actually we don't even need to sort out the last column, because we can take this idea of counting sort, how we, as I told you, it will make more sense if you actually know a bit about counting sort. We can take the idea of counting sort and use it here. And how will we do that? Is we can calculate where we can predict where in the first column a specific character will occur. And let's say how we can do that. So I have mentioned the indexes here, and I have mentioned a small little formula here. So let's take this T. How many characters can come before T? The first T. Let's say, so we know that 5 characters. There will be at least 5 characters. There will be exactly 5 characters before the first T in the first column occurs, or comes. And remember, we don't have this first column. We only have the last column here. We have not generated this first column by sorting. But we will still guess which position we need. So this T will come at least after 5 characters. And there is another information that we can use, that the order in the first column is maintained in the second column. So we know that we can also use the ranks here. We can use that we know that this 0th T will be the first T that occurs in the first column. This T with rank 1 will be the second T that occurs in the first column. The T with the rank 2 will be the third T that occurs in the first column. And that will help us in guessing which position should we look next. So let's take this T, right? We know that that there will be 5 characters before it. So number of characters before it will be 5. The rank will be 0. We know that it's the first T. So that will also be the first T in the first column. So that will be 5 plus 0, 5. And then we're adding 1. And why are we adding 1? To accommodate for the dollar, because we know that the first column always starts with dollar. So to accommodate that, we are shifting it by 1. And so 5 plus 1 is essentially 6. So we get this. We come to 6. And wait, this is T1, and this was also actually T1. So T1, we get to the character that we are looking for. And by the way, the property that we are talking about, like we were searching that T1 and we are matching the T1 same, and then we are looking at the character preceding it, that is known as the first last property of BWT, and that just makes it more interesting to decode the string. So as we saw that, let's just take a small example how we can do that. Let's say this one, I2 and 0, right? So the first column should have I2, but here we only have the last column, right? So n, and in the naive algorithm that I showed you before, what we will do, we will search for n here, and then we will get a here, and we will understand that a precedes n in the original string, but we don't have the first column here, so we will use our dear small formula. So we know that there will be 4 characters preceding a n. Okay, so, and we know that this n is the first n. There is only one n here, so we will take 0. So we'll add the rank, and we will add 1 just to accommodate the dollar, and we will get 5. And we can go here because, well, we have got the index 5, and we can come to the 5th index, and now we know that a precedes n in the original string. Now how will we go forward is, again, we will repeat our formula that we are trying to use to find the next step. So what is the number of characters before a? That is 0. Its rank here is 0, and then we add 1 to accommodate for the dollar, and we get 1. And you can see this is the a1 of the string, and we just jump to a1, and we can easily do this. We don't even need to sort it. With some ideas from counting sort, we can actually easily complete this decompression it in ON, and I hope this makes sense. If it doesn't, just write your questions down in the comments, and I'll address it with the best of my abilities. Right, and the thing that I'm leaving out a bit is suffix arrays, and I'll suggest that you take a look in those and learn about those. And again, I'll request you to not just learn this algorithm. After learning this algorithm, I request you to write stuff down, take some notes, write your thoughts, scribble something, put your thoughts in order, because this algorithm might be simple, but there are some nuances of it. And then go ahead and implement it in your favorite programming language, because that's when the understanding will set in stone in your mind. And I'd love to see your GitHub repos. If you decide to upload it to GitHub, I'll just love to see your GitHub repos in the comments, whatever programming language you think you should write it in. So I hope all this makes sense, and if you learn something new, please leave a like and subscribe to this channel, and do share it among your friends who you think might benefit from it, or just to give me some reach. Just share it, guys. Go ahead, share it. It will cost you nothing. Just share it. And with this beautiful note, I'll see you in the next video.